Okay, so now let's use this to prove some problems to be NP-complete. First, let's introduce the following problem, the Hamiltonian cycle problem. Or Ham cycle. So this problem, you are given a graph, and the problem is to determine whether there is a simple cycle in the graph that can visit all vertices. Okay. Which means, is there a traveling salesman tour? But now you are given a graph. In the Ham problem, you are given a graph and you are asked to determine if there is a simple cycle that goes through all vertices. While in the traveling salesman problem, the objective is different. In the traveling salesman problem, you are guaranteed to find a cycle that goes through all vertices. You are guaranteed to find a simple cycle that goes through all vertices. Why is that?
It is a complete graph.
Exactly, because it's a complete graph. So in the traveling salesman problem, because it's a complete graph, the input is guaranteed to be complete. You are guaranteed to find anything that you want, any kind of path, any kind of cycle that you want. So you are guaranteed to find a simple cycle that goes through all vertices. So there is no question about this. But now in the traveling salesman problem, we're trying to find a simple cycle that goes through all vertices and has minimum cost, with minimum cost in the optimization version, or with a cost that meets a certain target in the decision version of the traveling salesman problem. Okay? Now, the Hamiltonian cycle problem, given a graph, determine. So when I use the word determine, will this be then a decision problem or an optimization problem? Decision. So determine if yes or no, then it's a decision problem. Determine if the graph has a simple cycle that goes through all vertices. Okay, well, so let's look at some examples to understand the problem. So let's take an example of a graph that is Hamiltonian, for which the answer is yes. That's easy. So this is a graph that is Hamiltonian. A, B, C, D. This is Hamiltonian, and there is an obvious simple cycle that goes through all vertices, which is this. Now, you know, in order to illustrate the concept, we have to give an example of a graph that is not Hamiltonian. So this graph is not Hamiltonian. A, B, C, D, E. Okay. Now, can you find a simple cycle that goes through all vertices? You will not be able to. So if you try this, you start from A, then you go to B, then you go to C. Okay, so far we have visited A, B, C. Now we have a problem. Now we need to visit both E and D. And we cannot visit a vertex more than once. So if we go to E, we either go back, which is not allowed. So in order to get to D, we either go back or we go to A again. So in either case, we'll have to go through the same vertex more than once. And if we choose to go this way, we will just skip. If we go this way, we'll skip E. So there is no simple cycle that can go through all vertices. So this graph is not Hamiltonian. And this is Hamiltonian.
we assuming that the source is at A?
It doesn't matter. It's a cycle, so you can start from any vertex you want.
Oh yeah, that's right. 'Cause
It's a cycle, so you can start. Do you have a? Can you see a cycle that starts from another vertex?
no, because I remembered that you said it had to be a cycle. Because I was originally thinking you could go B, C, D, A, E, but then that's not a cycle because you can't go back to B. Yeah.
Yeah. So it's that. Well, it could be a cycle, but not a simple cycle. So you cannot find a simple cycle, right? You can find a non-simple cycle, a cycle that visits the same vertex more than once. But that's not what we want. We want a simple cycle. And so this is not a Hamiltonian. So this is an NP-complete problem. It doesn't have a polynomial time solution. So in this case, what's the brute force solution? What's the brute force solution to this problem? Yeah, so the brute force solution is to try
Everyone.
all possible paths. Yeah, all possible paths or all possible permutations. Some of the permutations may give you valid cycles, some of them may not, right? Because not any permutation will give a valid cycle or even a valid path because you may not have the edges for that. So you may or may not have the edges. But if you try all possible permutations, that's n factorial or v factorial. Okay. So this is a known NP-complete problem. Now, is this a decision or an optimization? This is a decision problem. Now, our example is, okay, so this is the example. Given that Hamiltonian cycle is known to be NP-complete, given that Ham cycle is known to be NP-complete, prove that TSP is NP-complete. Now, which form of TSP is NP-complete? Is it the decision or the optimization? The decision, yeah. The decision, TSP decision is NP-complete. Well, now we have to verify that traveling salesman problem satisfies both conditions. Now, this condition is easy, and we have just talked about it. So condition one, in order to prove that a problem is NP-complete, you have to prove that both conditions are correct. So condition number one, which is the polynomial time verifiability of traveling salesman decision, we have just said how to do that. You verify that all the vertices, the valid vertices, no repetition of vertices, and that the sum of edge weights on the proposed solution or proposed cycle, the sum of weights is less than or equal to the given target. Okay? So now this part, so we know it. So I'm not gonna write this down. So I'm gonna leave it for you to write it down. The interesting part is this. Of course, we're gonna use the blue condition, and we will be using Hamiltonian cycle as the problem that is known to be NP-complete to prove the NP-completeness of traveling salesman problem. So we need a reduction. We need a reduction from Ham cycle to TSP or TSP to Ham cycle. Yeah, from Ham cycle, from Ham to TSP. So we need to show that Ham Ham is polynomially reducible to TSP. Again, never get confused with these. So we are trying to show that there are multiple ways of interpreting this. You can easily look at the mnemonic, which is less than or equal. The less than or equal sign being used here is a very good mnemonic. It just means that this is known to be NP-complete. And the problem that I'm trying to prove, I'm going to prove that it's greater than or equal to this problem in terms of the level of difficulty. So that's how I will prove it. If I do the opposite, I will not be proving anything. Right? If you prove that it's easier, that the given problem is easier than a problem that is known to be NP-complete, that doesn't prove anything. Right? So I'm trying to prove hardness, not easiness. So this is one way of looking at this. Another way of looking at this is that this means that any instance of Ham cycle can be reduced to an instance of TSP. So this is what a reduction means, that given any instance of Ham cycle, you can reduce it to an instance of TSP, which means that if you have a solver for TSP, you can use it to solve Ham cycle. Now we'll see how. So you will assume that you have a solver for TSP. So this is TSP solver. Now what's the input to the TSP solver?
Graph.
What kind of graph? Complete graph. Complete graph. And a target. Okay, great. And it gives you a yes, no. Now, the question is, I am given a TSP solver. I give it a complete graph and a target. And it tells me whether there is a simple cycle with this target with cost that is equal to the target or less. Now, how can I use this to solve the Ham cycle problem? How can I use it so that if I give it this, it's going to tell me yes. And if I give it this is not Hamiltonian because it doesn't have all the edges. It's going to tell me no. So the reduction is about using a solver for one problem to solve another problem. Now, in order to employ this solver, first of all, I have to put the graph in the form that this solver expects for its input. So I have to make these graphs complete somehow. But I want to make them complete in a way that will serve my purpose, which is solving this problem. So how do I make them complete? And how do I select the target such that the TSP solver solves Ham cycle for me? Any instance of Ham cycle.
So the edges that exist in that graph should have a weight of 1, and the other edges that are needed to make it a complete graph should be more than 1, and the target should be the number of vertices.
Okay, great. So basically the idea is to find a way to distinguish between the edges that already exist in the graph and the edges that I will have to add in order to make it complete. So I can assign higher weights to the edges that I add. So I can do 1 and 2, and because I know that the number of that in the cycle, there will be exactly V edges will be selected. Or I can just do 0. I can give these a weight of 0, and I can add other edges and give them weights of 1. Now, what should be the target that I pass to traveling salesman in this case? What target should I give it?
0.
0, yeah. So now, if I give the traveling salesman solver, if I input this graph, right, and give it a target of 0, I'm asking it to find a simple cycle that visits all vertices, but with cost equal to 0 or less. So it will find a cycle with cost 0 only if it uses the original vertices, the original edges. If it finds a cycle that uses the original edges, it's going to meet the target of 0. If it needs to use other edges, then this means that there is no simple cycle that uses the original vertices, the original edges. So with this one here, so here it's going to find a 0. Here it's not going to find a 0 because it will have to use one of the added edges. Okay, so this is our first example of an NP-completeness reduction. Okay, so in this case, given a graph G, construct a graph G prime, or construct a complete graph G prime with the following edge weights. So the weight of edge U and V equals 0 if UV belongs to E, where E is the set of edges in the original graph. So technically, we should write G as a graph equals V and E. So a graph is a pair that consists of a set of vertices and a set of edges. Mathematically, that's what a graph is: a set of vertices and a set of edges. So E is the set of edges for G. Set of edges for G. And 1 if UV does not belong to E. Now, G prime has a TSP tour of cost 0 if and only if G is Hamiltonian. Okay, so this is how we describe this transformation. Now, by the way, this has to be a polynomial time reduction. So is this reduction polynomial in time? So basically, our reduction is constructing a complete graph. So when it's complete graph, we're talking about V squared. That's certainly polynomial. And these are basically, it's a V squared transformation. Right? We construct this complete graph, and these are the edge weights. So you have E, and E is not going to exceed V squared. So we're talking about a V squared. It takes V squared time to do the transformation from the given instance of Ham cycle into an instance of TSP. Okay, so any questions on this reduction? Yeah.
So essentially, when we reduce Ham to TSP, we're proving that TSP is harder by giving a solution for the TSP that will solve every instance of the Ham problem.
Okay, like I said, you can view this as, so as proving that TSP is harder, or by saying that if I can solve TSP in polynomial time, I will be able to solve Ham cycle in polynomial time. But I'm given that Ham cycle does not currently have a polynomial time solution. Therefore, I cannot have a polynomial time solution for TSP solver. Okay, so you can think of this as proof by contradiction as well, right? So you are given that Ham cycle is known to be NP-complete. So NP-complete means it does not currently have a polynomial time solution. Nobody knows a polynomial time algorithm for solving it. So now by reducing Ham to TSP, you are saying that if a polynomial time solution to TSP exists, I can use it to solve Ham. And this will contradict what you are given. You are given that Ham does not have a polynomial time solution, right? So this is, another way of looking at this. But the easiest way is to just think of the reduction as proving that the problem that you reduce to is harder or more general than the problem that you are reducing. So when you reduce Ham to TSP, you are basically showing that TSP is harder, is more general. Any instance of Ham can map to an instance of TSP. Yeah.
So even though we just proved that that Ham or TSP is harder than Ham, how does it prove that Ham is NP-complete? Is that just
We are given.
Oh.
We are given that. So given that Ham is known to be NP-complete. So we are assuming that we know that Ham is NP-complete. We are using this to prove that TSP is NP-complete. This is just an exercise, right? So we're not trying to prove a new problem to be NP-complete. Both problems are known to be NP-complete. But we are giving this example to show how you can prove one problem to be NP-complete given the fact that another problem is known to be NP-complete. Okay, so in practice, if you encounter one problem, you call it problem X, and you want to prove that X is NP-complete, you will look for a similar problem in the list of problems that are known to be NP-complete, and you will find a problem Y that looks similar or close to X, and then you reduce Y to X. And then you will prove that X is NP-complete. Okay?